Okay, what we have here, I've got MATLAB opened up. I wrote a script to generate some signals. Basically, I'm generating a random noise signal and also a sine wave, and then we're going to combine those two, and we're going to show time domain plots for both the noise and the sine wave, and also the combination, the sum of the two, and then we'll show some frequency domain plots of the same. So I'm not going to cover every detail of the script, but basically I've got, I define seconds equals 1. That is how long we want our signals to be in seconds. And I have defined SR, which is sample rate, to be 48,000 samples per second, which is a pretty common sample rate used in the audio world. Then I have some things here that are necessary to do the sine wave. Frequency 1000, that's the frequency of the sine wave. Right here, this line here is actually generating, using MATLAB's RANDN function, a chunk of noise. So each of these 48,000 points will represent each one is a random noise sample. So basically we've got N1 is going to contain 48,000 different random numbers in it. This is PTS is points. That's how many points I want to do in the plots, rather than typing it in every time if I want to change them all. So down here, I'm going to actually, we're going to generate the signals. So I define sig1, that's going to be my sine wave. So I've got the equation in here, and that's going to generate our 1000 hertz sine wave. And then down here, I make our signal SN1, which is basically the sine wave, sig1, which is this piece, and then N1, which was up here. So basically I'm adding that and defining it as SN1. Next, in this section, I take the FFT. So we're going from time to frequency domain. Uppercase is traditionally used to represent frequency domain, lowercase for time domain. And then I'm going to do some plots here. So I've got 5 figures. So I'm going to plot just the noise, and I go from 1 to PTS was up here as, where to go, 200. So I don't want to plot all 48,000 points. I just want to look at some of them. So 1 to 200. Then for the sine wave, I'm doing again 1 to 200. And I set up an axis here, limits. And then down here, I'm doing the same thing, another plot, time domain plot of the combination, the sum of the noise and the sine wave. And then these final plots, I basically do an FFT plot in dB of just the signal, that's the sine wave, and then I do the FFT of the sum of the sine wave and the noise. So if I run this, go up here and click run, and it's going to do its thing. It's going to generate some figures. So what I'm going to do is I'm going to move these around and arrange them in a particular order. So I'll put figure 1 there, 2, 3. All these up top here are time domain, and then this one and this one are frequency domain. So what do you see here is this is the random noise signal, the first signal we generated, and you can see all these are, technically they're all dots connected by a line. You can see the first 200 points, yeah, it's kind of all over the place. Our sine wave, as we expect, follows a nice pattern, and in this particular case, I had it peak out at a value of 1. And then the sum of those is basically this plot and this plot here added, and you can kind of see the sine wave in here, but the noise is superimposed onto it. So they're both there. Each one of them is unchanged, but now they're added together. So this is your total sum. Now down here, I've taken an FFT of the sine wave, and now this number down here, this, I don't know, 225 or whatever dB, that is the mathematical noise floor of the computation. That's the limit of the math in the computer. If I look at the sine wave peak up here, it comes out to 87.6042. I go over here. It's a little bit higher, 87.6647. So why would that be higher? Because this noise, actually this noise here, does have a frequency component at 1000 hertz, where the sine wave is. So if you add those together, you're going to get a little bit more here, but the contribution is very, very small. But notice the noise floor, that it kind of has a wide swath, because that's just one average. But somewhere's in the, if this is 80 something, this is, I don't know, 45. You got about a 40 something dB signal to noise ratio here. Even though as cruddy as this looks, it's really actually pretty good. This signal clearly sticks out of here. So that's the first thing we wanted to show on this video, and we'll pick up with the next segment shortly. All right, I've got another MATLAB script here, and what this one is going to deal with is random noise, and we're going to talk about random noise sequences and how they add up. So this script, I got some stuff in it that doesn't even matter, but the main part of it is right in here. You can see that I have, we'll just look at one of them. I've declared these variables like n1 through n10, and what it's going to do, each of these lines is going to generate a random number sequence from 1 to 48,000 based on these numbers up here. So each of these 10 lines is going to be a variable, or I'm assigning it like n1 through n10, and we're going to have 10 of those variables, and each one is going to contain a set of random numbers, and they're all independent of each other, because every time you run MATLAB's RANDN command, it's going to generate a different sequence. You're not going to get the same one over and over again. That would be wouldn't be a random number generator if it was like that. So then what I do next is MATLAB STD command, standard deviation. If you have a signal that has no DC offset, and these don't, random number signals, they're plus and minus around 0, STD basically gives you the RMS value of the numbers in that sequence. So I've got 10 lines here, and I'm basically going to generate the RMS value of each of those 10 sets of noise. And then down here what I do is I take all 10 of these sequences that we generated up here, and I'm adding them, and I'm calling that n sum. So that's just the sum of all of these things added together. And then I'm going to take the RMS of that sum, and you're going to see some interesting things happen here. So there's no plots with this one, but if I go ahead and run it, we come down to this other window here. I'm going to make this a little bigger. You can see N1 RMS 0.993, N2 0.9965. They all, in a perfect world, they'd all be 1. You look at them and they're all a little different. So why is that? When you're dealing with noise, every sequence is a little different, and you won't quite get 1 unless the sequences are extremely long. In this case, they're 48,000 samples long. So it's reasonably consistent. But if you come down here, and then when I add them all up, intuitively you might think, well, if I add 10 of those signals together and they all have an RMS value of 1, I should get an RMS value of approximately 10. But that's not the case. Down here you're going to see 3.1678. Now watch, if I run this again, look at this number. It's a little different. I'll run it again. A little different still. Again, that's because we're dealing with noise, and every time they're going to be a little different. So how can we get that smoother? What we can do is come up here in the script, and where I have seconds equals to 1, I'm going to make it 100. So now instead of 48,000, I've got 4.8 million random noise samples in each of these variables. Now, if I run it, it's going to take a lot longer because it's making the computer work. But now, if you look at the numbers, the RMS numbers, see how they're kind of convening closer to 1? They're getting closer and closer and closer. They're not exactly, but they're more clean than they were. And down here, 3.1622. So we'll run this again. A little bit different, not terribly. We'll run this again. And if we run it again, you see they're coming out pretty close. And I want you to know something interesting. If I take a square root of the number 10, see this number here? That's square root of 10. Look at this number. Pretty close. So we'll get to what that means in a minute. But if I add 10 random noise signals together, I get an RMS value. And I should say that the RMS value of each one of these noise signals is pretty close to 1. But they do not add up coherently because each one is random. So sample by sample, they're not going to add up in a consistent way. And they come up to, this number, which is really, really close to the square root of 10. If I was to go up here and change my variable, what do we have, 100 up here? Let's change it to 1,000. I don't know how long it's going to take to run, but we'll try it. Hit run. Computer's going to crank away at that. See, it's taking a lot longer. The numbers are closing in. So the longer you make that, the closer it's going to be. And if I do square root of 10 again, it's getting pretty close. And again, if you made those longer and longer, ideally it would close in on that. So keep that thought for a minute, and we'll come back to the next section after I generate it. All right, so we just talked about adding up random noise sequences, and we showed that if you have 10 random noise signals, all of the same RMS value, which is 1 nominally, we add them all up. We do not get 10 volts. We get about the square root of 10, which is 3.1623, well, yeah, pretty close. So now imagine if we had 10 sine waves of the same frequency and the same amplitude. If we were to add those up, you're going to get a value of 10. So compared to any one signal, which is 1, and you have 10 of them, you add them up, you get 10, you've got a gain of 10, or if we go down here and do equals 20 star log 10 of 10. Oops, I'm thinking of Excel. I got to get rid of the. We come up with 20. So if we have a single sine wave of 1 volt, but we add 10 of them together, we end up with a result of 10 volts. That in dB is a 20 dB gain over any single one of those sine waves. Now remember, we added the noise, but we didn't get 10. We got roughly the square root of 10. So if I go 20 star log 10 of square root of 10, oops, 10, I get the number 10. So that's 10 dB. So if you look here, when we did the sine wave, adding 10 of them, we got a value of 20 dB. When we add the noise, we got 10. So if we were to add, if we had the sine wave at 1 volt RMS and the noise at 1 volt RMS, that is effectively a signal to noise ratio of 0 dB. But if we add 10 random noise sources, they have to be random, that's very important, and the same amplitude, and we add 10 sine waves of the same amplitude and frequency, all in phase, we get a value of 10, but the gain, the signal to noise gain, is 10 dB. And that is one of the concepts that you will need to understand if you are trying to understand beamforming. So we'll go into more of that later. There's a lot more to this, but this is a start.